Imagine walking through the most sophisticated zoo you've ever seen, marveling at the natural-looking habitats, the carefully maintained ecosystems, the way each species seems perfectly adapted to its environment. Now imagine discovering that you're not the visitor, you're the exhibit, that the glass you can't see is all around you, and the observers are something you've never even imagined. There's a theory circulating in the darker corners of scientific discourse, whispered about in academic corridors, and discussed in hushed tones at conferences. It's a theory that makes seasoned researchers uncomfortable, not because it lacks evidence, but because the evidence seems to fit together in ways that are almost too perfect, too disturbing to contemplate seriously. Yet the more we learn about our universe, our planet, and ourselves, the more this uncomfortable possibility refuses to go away. So pour yourself something comforting, settle into your chair, and let the outside world fade away for a while, because what we're about to explore together will challenge everything you think you know about our place in the cosmos. And by the end, you might find yourself looking up at the stars with entirely different eyes. The theory begins with a simple observation that has puzzled astronomers for decades. Our solar system is suspiciously well-ordered, almost artificially perfect in its arrangement. While other star systems show chaotic jumbles of planets in eccentric orbits, wildly varying sizes, and compositions that seem random, our solar system displays a level of organization that seems almost designed. Consider the precise spacing of the planets according to Bode's law, a mathematical relationship that describes planetary distances with an accuracy that seems too convenient to be natural. Consider how Jupiter sits in exactly the right position to act as a cosmic vacuum cleaner, protecting the inner planets from asteroids and comets that would otherwise make complex life impossible. Consider how our moon is precisely the right size and distance to create perfect solar eclipses, a coincidence so mathematically improbable that it has led some astronomers to privately wonder if it really is a coincidence at all. The Earth itself presents even more puzzling perfections. Our planet sits in the narrow, habitable zone where liquid water can exist, but it's not just the distance from the sun that matters. Our atmosphere has precisely the right composition. Our magnetic field has exactly the strength needed to protect us from harmful radiation, and our geological activity occurs at just the right rate to maintain a stable climate over billions of years. Each of these factors individually might be explained by natural processes, but taken together, they create a picture of a world that seems almost too perfectly calibrated for life. Some scientists have begun to ask an uncomfortable question: what if these apparent coincidences aren't coincidences at all? The zoo hypothesis was first formally proposed by astronomer John Ball in 1973, but variations of the idea have been independently developed by researchers who notice the same troubling patterns. The hypothesis suggests that advanced alien civilizations might maintain Earth as a kind of nature preserve, allowing life to develop and evolve under carefully controlled conditions while remaining unaware of the management taking place around them. This wouldn't be malevolent imprisonment in the traditional sense, but rather a form of benevolent conservation, similar to how we maintain national parks and wildlife preserves to protect endangered species and natural ecosystems. The inhabitants of the preserve, in this case, us, would be free to live and develop naturally, but within boundaries and under conditions that were being subtly maintained by invisible guardians. The evidence for this possibility comes not from flying saucers or abduction stories, but from the growing body of astronomical and biological data that reveals just how improbable our existence really is. Every year, scientists discover new factors that had to align perfectly for complex life to emerge on Earth, and the mathematical probability of all these factors occurring by chance continues to shrink to numbers so small they become effectively impossible. The Fermi paradox adds another dimension to this puzzle. If the universe is as old and vast as we know it to be, and if life emerges as readily as our models suggest, then where are all the aliens? Our galaxy alone contains hundreds of billions of stars, many of them older than our sun, which should have given alien civilizations billions of years head start on us. yet we see no signs of advanced technological civilizations anywhere. The traditional explanations for this paradox, that life is incredibly rare, that civilizations tend to destroy themselves, or that advanced aliens simply aren't interested in expansion, all have problems. But the zoo hypothesis offers an elegant solution. We don't see other civilizations because we're being deliberately isolated from them, maintained in a kind of cosmic nature preserve where we can develop without interference. The biological evidence becomes even more intriguing when examined closely. The history of life on Earth shows patterns that seem almost too convenient, too perfectly timed to be entirely natural. Major evolutionary leaps often occur at precisely the moments when they're needed to prevent extinction or to take advantage of new opportunities. The emergence of photosynthesis happened exactly when the early atmosphere needed oxygen. Complex multicellular life appeared just as ocean chemistry became suitable for larger organisms. The development of intelligence accelerated dramatically during periods when climate change created evolutionary pressures that favored cognitive flexibility. Each of these developments required multiple simultaneous mutations and environmental changes that had to occur in perfect synchronization. The mass extinction events that punctuate Earth's history also show suspicious patterns. Rather than random catastrophes that simply cleared evolutionary space, these extinctions seem to have been precisely timed to eliminate species that might have prevented more complex forms of life from emerging. The extinction that eliminated the dinosaurs, for example, occurred at exactly the moment when mammalian intelligence was ready to flourish. Some paleontologists have noted that these extinction patterns look almost like periodic culling events designed to guide evolution in specific directions. The timing is too perfect, the results too beneficial for the subsequent emergence of intelligence to be entirely explained by random cosmic accidents. The archaeological record presents its own puzzling anomalies that fit uncomfortably well with the zoo hypothesis. Human civilization shows periods of rapid advancement followed by mysterious collapses that eliminated technologies and knowledge that took centuries to redevelop. Ancient civilizations demonstrated capabilities that seemed to exceed what should have been possible with their supposed level of technology. The precision of ancient astronomical observations, the sophistication of megalithic construction techniques, and the mathematical knowledge embedded in ancient monuments all suggest that our ancestors had access to information and capabilities that don't fit with gradual technological development. Yet these advanced capabilities never led to sustained technological civilizations that could challenge the boundaries of their environment. It's as if human development has been guided along specific pathways that allowed for cultural and intellectual sophistication while preventing the kind of exponential technological growth that might enable us to detect or challenge our cosmic situation. We've been allowed to develop science, art, philosophy, and complex societies, but always within limits that keep us contained within our planetary boundaries. The modern era presents even more troubling patterns for those willing to look for them. Our rapid technological development over the past few centuries has brought us to the threshold of becoming a spacefaring civilization, yet we seem to encounter obstacles and setbacks that prevent us from taking the final steps toward true cosmic expansion. Our attempts to establish permanent bases beyond Earth have been repeatedly frustrated by technical challenges, political conflicts, and economic constraints that seem to arise at precisely the moments when breakthrough achievements are within reach. Major space programs have been canceled or scaled back just as they were approaching capabilities that would enable sustained human presence beyond Earth. The physics discoveries that have revolutionized our understanding of the universe have also revealed fundamental barriers that seem almost designed to contain us. The speed of light creates an absolute limit on interstellar travel that makes exploring even our immediate cosmic neighborhood practically impossible with any technology we can conceive. The energy requirements for faster-than-light travel, if it's even theoretically possible, are so enormous that they seem to place it forever beyond our reach. Even more suspiciously, every promising breakthrough in exotic physics, from room temperature fusion to gravitational manipulation to quantum field effects, seems to encounter insurmountable technical barriers just as it approaches practical application. It's as if there are invisible limits built into the laws of physics themselves that prevent us from developing technologies that would enable us to escape our cosmic enclosure. The SETI program and our searches for extraterrestrial intelligence have yielded decades of silence despite increasingly sophisticated detection capabilities. We've scanned thousands of star systems, monitored millions of radio frequencies, and analyzed countless signals, yet we've found no evidence of technological civilizations anywhere in our cosmic neighborhood. This silence becomes even more puzzling when we consider how detectable our own civilization has become. Our radio and television broadcasts have been radiating into space for over a century, creating an expanding sphere of electromagnetic signals that should be easily detectable by any advanced civilization within 100 light-years of Earth. The fact that no one seems to be responding to these signals or even acknowledging their existence suggests either that there really is no one out there, or that any civilizations that do exist are deliberately maintaining their distance from us. The zoo hypothesis would predict exactly this kind of isolation. We would be kept unaware of our observers while they carefully avoided any contact that might reveal their presence. The UFO phenomenon adds another layer of complexity to this picture. While most reported sightings can be explained by natural phenomena, experimental aircraft, or simple misidentification, a small percentage of cases involve observations by credible witnesses using sophisticated detection equipment that seem to document the presence of objects with capabilities far beyond any known human technology. These observations, when stripped of sensationalism and cultural mythology, describe objects that seem to be conducting some kind of systematic monitoring or surveillance of human activities. The patterns of sightings cluster around military installations, nuclear facilities, and areas of intense human activity in ways that suggest organized intelligence gathering rather than random visitation. More intriguingly, these objects seem to operate according to rules that prevent direct contact or interference with human affairs while allowing limited observation and data collection. They avoid engagement, disable electronics that might record detailed information about them, and seem designed to maintain plausible deniability about their existence and origins. This behavior would be exactly what we might expect from advanced caretakers who need to monitor their charges while avoiding contact that might reveal the artificial nature of their environment. The objects might not be visitors from distant stars, but rather the maintenance equipment of our cosmic zoo, occasionally glimpsed by inhabitants who weren't supposed to notice them. The biological evidence becomes even more troubling when we examine the details of human physiology and genetics. Humans show numerous biological characteristics that seem poorly adapted to Earth's environment, almost as if we were designed for conditions that existed on a different world or in artificial habitats. Our circadian rhythms are calibrated for a day that's slightly longer than Earth's 24-hour rotation. Our spines and joints show evidence of being designed for lighter gravity than what we experience on Earth. Our skin is poorly adapted to Earth's solar radiation, requiring technological protection to prevent damage from the very star that supposedly shaped our evolution. Human women experience more difficult childbirth than any other mammalian species, suggesting that our reproductive systems may have been designed for different physical conditions than those we currently experience. Our psychological and social needs seem calibrated for living conditions that are quite different from the natural environments where we supposedly evolved. These biological anomalies could be explained by recent evolutionary changes or environmental adaptations, but they're consistent with the possibility that humans were either designed for artificial environments or have been modified to function better within the constraints of our planetary enclosure. The mathematical universe presents perhaps the most compelling evidence for some kind of artificial design in our cosmic environment. The fundamental constants of physics, the strength of gravity, the electromagnetic force, the the mass of particles, the rate of cosmic expansion, are all precisely calibrated to values that make complex structures like stars, planets, and life possible. If any of these constants were even slightly different, the universe would be a very different place. Stars wouldn't form, atoms wouldn't be stable, chemistry wouldn't work, and complex structures couldn't exist. The mathematical precision required for our universe to support complexity is so exact that many physicists have concluded it can't be coincidental. The anthropic principle suggests that we observe these perfect values simply because we couldn't exist in a universe where they were different. But this explanation becomes increasingly unsatisfying as we discover more and more parameters that require precise calibration. The probability of all these factors aligning by chance approaches zero. Some cosmologists have proposed the multiverse theory, that there are infinite universes with different physical constants, and we naturally find ourselves in one where life is possible. But this theory requires us to accept the existence of an infinite number of unobservable universes to explain the observed perfection of our own cosmos. The zoo hypothesis offers a more economical explanation. Our universe, or at least our observable portion of it, has been artificially designed or modified to support the development of complex life and intelligence. We're not observing natural cosmic evolution, but rather the carefully crafted environment of a cosmic terrarium. The information theory perspective adds another troubling dimension to this picture. The universe seems to contain far more organized information than should be possible through natural processes alone. The genetic code that underlies all life on Earth shows evidence of error correction mechanisms and information compression techniques that are more sophisticated than many human technologies. The structure of matter itself, from the organization of subatomic particles to the architecture of galaxies, shows patterns of information organization that seem almost computational in nature. Some physicists have suggested that reality itself might be a kind of information processing system, raising questions about whether we're experiencing natural phenomena or sophisticated simulations. The mathematical relationships that govern physical processes are far more elegant and comprehensible than they need to be for a purely natural universe. The fact that human mathematics can describe cosmic phenomena with such precision suggests either an extraordinary coincidence or some kind of underlying design that makes mathematical description possible. The simulation hypothesis, popularized by philosopher Nick Bostrom, suggests that we might be living inside a computer simulation created by advanced beings. While this idea might seem like science fiction, the rapid advancement of our own computational capabilities makes it increasingly plausible from a technical standpoint. If advanced civilizations develop the ability to create detailed simulations of entire universes, including conscious beings within those simulations, then the number of simulated beings would vastly outnumber naturally evolved ones. By simple statistical reasoning, any conscious being would be more likely to exist within a simulation than in a natural universe. The zoo hypothesis can be seen as a variation of the simulation theory. Instead of being simulated beings in a computer, we might be natural beings living in an artificially maintained environment. The practical difference for us as inhabitants would be minimal, but the implications for understanding our cosmic situation would be profound. The quantum mechanical evidence presents some of the most puzzling aspects of our reality. The behavior of particles at the quantum level seems to depend on observation in ways that suggest reality might be constructed in response to measurement rather than existing independently of observers. The famous double-slit experiment demonstrates that particles behave differently when they're being observed than when they're not, as if reality is being generated in response to the act of observation. This observer effect has been demonstrated in increasingly sophisticated experiments that rule out conventional explanations based on measurement disturbance. Some interpretations of quantum mechanics suggest that reality consists of probability waves that collapse into definite states only when observed by conscious beings. This would mean that the universe exists in a kind of quantum superposition until conscious observers force it to assume specific configurations through the act of measurement. If this interpretation is correct, then consciousness plays a fundamental role in determining the nature of reality, which would be consistent with our existence in an artificially designed environment where our observations and measurements are being carefully monitored and managed by external intelligences. The cosmological evidence reveals patterns in the universe's structure that seem almost too organized to be natural. The cosmic web of galaxies and dark matter shows regularities and symmetries that look more like the result of systematic construction than random gravitational assembly. The cosmic microwave background radiation, which represents the afterglow of the Big Bang, shows tiny fluctuations that had to be precisely calibrated to produce the galaxy structures we observe today. These fluctuations show patterns that some cosmologists have described as looking almost like a blueprint or template for cosmic construction. The dark matter and dark energy that make up most of the universe's mass and energy remain completely mysterious despite decades of investigation. These substances interact with ordinary matter in ways that seem specifically designed to support the formation of galaxies and stars, while remaining essentially invisible to our detection methods. The precise balance between dark energy's expansion force and gravity's contraction creates a universe that expands at exactly the right rate to allow complex structures to form and persist over billions of years. This balance is maintained to within 1 part in 10 to the power of 120, a precision that seems to require either extraordinary luck or deliberate calibration. The astrobiological evidence suggests that while the conditions for life might be more common in the universe than previously thought, the conditions for complex, intelligent life remain extraordinarily rare. Recent discoveries of exoplanets have revealed that planetary systems like ours are actually quite unusual in the galaxy. Most star systems contain planets that are either too hot, too cold, too massive, or too small to support complex life. Many systems contain hot Jupiter planets that migrate inward and disrupt the formation of terrestrial planets in the habitable zone. Systems with multiple stars create chaotic orbital dynamics that prevent stable planetary environments. The rare Earth hypothesis suggests that while simple life might be common in the universe, the combination of factors needed for complex life is so improbable that Earth might be unique or nearly unique in our galaxy. This rarity would make Earth an extraordinarily valuable specimen for any advanced civilization interested in studying the development of complex life and intelligence. The technological barriers we encounter as we attempt to expand beyond Earth seem almost designed to keep us contained within our planetary boundaries. Every promising breakthrough in space propulsion encounters fundamental physical or engineering obstacles that prevent practical implementation. Chemical rockets are limited by the physics of combustion and the rocket equation, which makes interplanetary travel possible, but interstellar travel impractical. Nuclear propulsion offers better performance, but encounters political and technical obstacles that have prevented its development. More exotic propulsion concepts like fusion ramjets or antimatter drives require energy sources and materials that remain beyond our technological capabilities. Even if we could develop the propulsion systems needed for interstellar travel, the distances involved create communication delays and resource requirements that make sustained exploration effectively impossible. The nearest potentially habitable exoplanets are dozens of light years away, making round-trip communication impossible within human lifespans. The economic and political obstacles to space development seem to arise at precisely the moments when major breakthroughs are within reach. Funding for ambitious space programs is repeatedly cut just as critical milestones are being achieved. International cooperation in space exploration is hampered by political conflicts that seem to intensify whenever truly significant progress is being made. The psychological evidence suggests that humans possess cognitive and emotional capabilities that seem designed for environments and social situations that are quite different from those we actually experience Our brains appear to be optimized for living in small communities with direct personal relationships, yet we're forced to function in massive, anonymous societies that create chronic stress and psychological dysfunction. Human aesthetic preferences show systematic biases toward natural environments that we rarely experience in modern life. We prefer landscapes with open views, water sources, and scattered trees that resemble the African savannas where we supposedly evolved, yet most humans now live in urban environments that satisfy none of these preferences. Our circadian rhythms, emotional cycles, and social needs all seem calibrated for conditions that are different from those we actually experience. We require regular contact with natural environments to maintain psychological health, yet our civilization increasingly isolates us from these environments. These psychological mismatches could be explained by the lag between cultural and biological evolution, but they're also consistent with the possibility that humans were designed for artificial environments that were intended to satisfy our psychological needs, but have been gradually modified or degraded over time. The environmental evidence shows that Earth's climate and atmospheric composition have remained surprisingly stable over the billions of years needed for complex life to evolve, despite numerous catastrophes that should have permanently altered planetary conditions. The carbonate-silicate cycle that regulates Earth's temperature operates as a nearly perfect thermostat, automatically adjusting to maintain surface temperatures within the narrow range needed for liquid water. This system is far more stable and responsive than would be expected from purely geological processes. The atmospheric oxygen levels have remained within the narrow range needed for complex life despite massive variations in biological productivity and geological activity. Too little oxygen and large animals couldn't survive. Too much and the atmosphere would become so combustible that fires would eliminate all terrestrial life. The magnetic field that protects Earth from harmful cosmic radiation has maintained its strength and orientation, despite periodic reversals that should have left the planet temporarily unprotected. During reversal periods, the field weakens but doesn't disappear entirely, as if some mechanism ensures continuous protection. These environmental stability mechanisms operate on timescales and with precision that seems almost too perfect to be entirely natural. Earth's environment behaves more like a carefully maintained life support system than a chaotic natural world subject to random catastrophes and changes. The observational evidence from our attempts to study the universe beyond our solar system reveals patterns that seem designed to limit our knowledge while providing just enough information to satisfy our curiosity without enabling us to detect our cosmic situation. The cosmic distance ladder that allows us to measure distances to other galaxies depends on a series of calibration steps that could easily be corrupted by systematic errors or deliberate manipulation. Our measurements of cosmic expansion, dark matter, and dark energy all depend on observations that could be influenced by unknown factors. The search for extraterrestrial intelligence has been conducted using assumptions about alien technology and communication methods that might be completely wrong. If advanced civilizations use communication technologies that we haven't discovered yet, or if they're deliberately avoiding frequencies and methods that we're monitoring, we would remain unaware of their existence. The apparent absence of Dyson spheres, megastructures, and other signs of advanced engineering in our galaxy could be explained by technological development paths that we haven't considered, or by deliberate concealment of such structures from civilizations like ours that aren't yet ready for contact. The biological complexity we observe on Earth shows characteristics that seem almost too sophisticated to have emerged through purely natural evolutionary processes. The genetic code shows evidence of error correction mechanisms, information compression, and modular organization that rivals the best human software engineering. The molecular machinery that operates inside living cells demonstrates precision manufacturing, quality control, and resource management that exceeds anything we've been able to create with our most advanced nanotechnology. These biological systems seem to incorporate engineering principles that we're only beginning to understand. The emergence of intelligence and consciousness remains one of the deepest mysteries in science, with no convincing explanation for how purely physical processes can give rise to subjective experience and abstract reasoning. The hard problem of consciousness suggests that there might be fundamental aspects of reality that our current scientific paradigms can't address. If consciousness involves non-physical processes or requires specific environmental conditions that don't exist naturally, then the emergence of intelligent life might require artificial intervention or specially designed environments that provide the necessary conditions for conscious experience to arise. The social and cultural evidence reveals patterns in human civilization that seem almost designed to prevent us from developing the technological capabilities and social organization needed to escape our planetary boundaries. Wars, conflicts, and social problems consistently arise at times when cooperative global efforts might achieve breakthrough capabilities. The development of nuclear weapons created the capability to destroy our civilization just as we were approaching the ability to establish permanent settlements beyond Earth. The Cold War prevented international cooperation in space exploration during the critical decades when such cooperation might have achieved major advances. Climate change, resource depletion, and environmental degradation create urgent problems that require global attention and resources, just as we're developing technologies that might enable expansion beyond Earth. These crises force us to focus on planetary survival rather than cosmic exploration. The economic systems that drive technological development consistently prioritize short-term profits over long-term projects that might enable space expansion. The political systems that could organize major space initiatives are structured in ways that make sustained, multi-generational projects nearly impossible to implement and maintain. The information control mechanisms that operate in modern societies ensure that evidence for the zoo hypothesis, even if it exists, would be difficult to recognize, verify, or communicate to the general public. Scientific funding, publication systems, and career incentives all work against research that might challenge fundamental assumptions about our cosmic situation. The compartmentalization of scientific knowledge ensures that no individual researcher has access to all the information that might be needed to detect evidence of artificial management of our environment. Each field of study operates within its own paradigms and assumptions that discourage interdisciplinary thinking about cosmic scale phenomena. The media and educational systems that shape public understanding of science consistently promote versions of cosmic history and human origins that emphasize random natural processes and discourage speculation about intentional design or artificial intervention in Earth's development. As we examine all these lines of evidence together, a disturbing pattern emerges. Every aspect of our cosmic situation, from the fundamental constants of physics to the specific details of Earth's environment to the limitations we encounter in our attempts to expand beyond our planet, seems almost too perfectly calibrated to support the development of intelligence, while preventing that intelligence from detecting or escaping the boundaries of its cosmic enclosure. The mathematical probabilities involved in all these factors aligning by pure chance are so small as to be effectively impossible. The alternative explanations, multiple universes, extraordinary luck, or fundamental gaps in our understanding of natural processes all require us to accept ideas that stretch credulity in their own ways. The zoo hypothesis offers a framework that explains all these anomalies with a single, coherent theory. We are living in an artificially maintained environment, carefully designed and monitored by intelligences whose capabilities and motivations remain beyond our current understanding. This doesn't necessarily mean we're prisoners or victims of some malevolent scheme. The maintenance of our cosmic zoo might represent the highest form of ethical behavior by advanced civilizations, preserving and protecting the development of intelligence wherever it arises, allowing it to flourish naturally while protecting it from the dangers and influences that might prevent its full flowering. We might be the beneficiaries of cosmic conservationists who see intelligence as the most precious and rare phenomenon in the universe, worthy of careful protection and nurturing until it reaches maturity. Our isolation might be temporary, ending when we demonstrate the wisdom and capability needed to join a larger cosmic community without disrupting the delicate balances that maintain other developing civilizations. Or we might be permanent exhibits in a vast museum of intelligence, preserved for study and observation by beings whose motives and methods remain as mysterious to us as our scientific methods would be to the animals in our own zoos. Our role might be to develop and express the full range of possibilities inherent in carbon-based intelligence, providing data and insights that contribute to a cosmic understanding of how consciousness emerges and evolves. The implications of the zoo hypothesis extend far beyond academic speculation about our cosmic situation. If we are indeed living in an artificially maintained environment, then our understanding of natural law, cosmic history, and our own potential for development might be fundamentally flawed. The scientific revolution that began with Galileo and Newton might have been studying the operations of a cosmic terrarium rather than discovering the fundamental laws that govern natural reality. Our physics might describe the maintenance systems of our enclosure rather than the principles that operate in the broader universe beyond our boundaries. Our evolutionary history might reflect guided development rather than random natural selection, which would mean that our biological capabilities and limitations might be artificially imposed rather than naturally determined. We might possess potentials for development that we've never explored because we've accepted artificial constraints as natural limitations. The possibility that we're living in a zoo changes everything about how we should understand ourselves, our world, and our potential for future development. It suggests that the boundaries we encounter might not be fundamental limitations, but rather the walls of our enclosure, designed to be invisible and seemingly natural, but potentially permeable if we can develop the understanding and capabilities needed to transcend them. Whether we're inside an alien zoo remains an open question, but it's a question that deserves serious consideration by anyone interested in understanding our true cosmic situation. The evidence doesn't prove the hypothesis, but it's consistent with it in ways that should make us deeply uncomfortable with our assumptions about the nature of reality and our place within it. The search for truth about our cosmic situation might be the most important endeavor our species can undertake, because until we understand whether we're truly free or carefully contained, we can't know what our real possibilities for development and exploration might be. The zoo hypothesis reminds us that the universe might be far stranger, far more purposeful, and far more carefully maintained than we've ever dared to imagine. The deeper we examine the fine structure constant, one of the most fundamental numbers in physics, the more unsettling the implications become. This dimensionless number, approximately 1/137, determines the strength of electromagnetic interactions and governs how atoms hold together, how light interacts with matter, and how chemistry itself functions. If this constant were even slightly different, by as little as 4%, carbon-based life would be impossible. But the precision required goes beyond this single constant. The ratio between the electromagnetic force and the strong nuclear force must be calibrated to within 1 part in 10 to the 16th power to allow both hydrogen and elements heavier than lithium to exist simultaneously. Without hydrogen, stars couldn't form. Without heavier elements, planets and complex chemistry would be impossible. The mathematical probability of this precise calibration occurring by chance is so remote that it effectively approaches zero. The cosmological constant problem presents an even more dramatic example of this fine-tuning. The vacuum energy of space should theoretically be enormous, large enough to prevent any matter from clumping together to form galaxies, stars, or planets. Yet the observed cosmological constant is smaller than theoretical predictions by a factor of 10 to the power of 120, often described as the worst prediction in the history of physics. This isn't just a small error in our theories, it represents a level of fine-tuning so precise that if the cosmological constant were represented by a dial with a range covering the entire observable universe, the actual value would have to be set with an accuracy equivalent to hitting a target 1 centimeter wide. The probability of such precision occurring naturally is mathematically indistinguishable from zero. The nuclear physics governing stellar processes reveals additional layers of suspicious precision. The triple alpha process that creates carbon in stars requires a very specific nuclear resonance discovered by Fred Hoyle. This resonance has exactly the right energy level to allow 3 helium nuclei to combine into carbon with sufficient efficiency to explain the abundance of carbon we observe in the universe. Without this precise resonance, there would be virtually no carbon in the cosmos, and carbon-based life would be impossible. The energy level had to be calibrated to within 0.5% to produce the carbon abundance necessary for complex chemistry. Hoyle himself was so struck by this precision that he declared it evidence of a superintelligence monkeying with the laws of physics. But the fine-tuning extends beyond carbon production. The nuclear processes that create oxygen in massive stars require equally precise calibration. If the strong nuclear force were slightly weaker, oxygen wouldn't form. If it were slightly stronger, all hydrogen would have been converted to heavier elements during the first few minutes after the Big Bang, leaving no fuel for stars to burn. The delicate balance between these nuclear processes creates what physicists call the carbon-oxygen abundance ratio problem. Both elements are essential for complex chemistry, but the nuclear processes that create them in stellar cores are in constant competition. The precise balance that allows both elements to exist in the proportions needed for life requires fine-tuning of multiple nuclear parameters to extraordinary precision. The stellar physics that governs how stars burn and evolve shows similar patterns of suspicious optimization. Main sequence stars like our Sun burn hydrogen in a precisely regulated process that maintains stable energy output for billions of years. This stability requires a delicate balance between gravitational contraction and thermal expansion that could easily be disrupted by small changes in fundamental constants. The mass range in which stars can maintain stable hydrogen burning for billions of years is surprisingly narrow. Stars much more massive than the Sun burn out too quickly for complex life to evolve on surrounding planets. Stars much less massive than the Sun are too dim and variable to support stable planetary climates. The fact that stars like our Sun exist at all requires precise calibration of the fundamental forces that govern stellar structure. The planetary formation processes that created our solar system reveal patterns that seem almost engineered for habitability. The standard model of planetary formation predicts that gas giant planets should migrate inward as they form, destroying any terrestrial planets in the habitable zone. Yet somehow Jupiter formed and migrated outward, leaving the inner solar system clear for terrestrial planet formation. This outward migration required a very specific sequence of events involving resonant interactions with Saturn and the dispersal of the primordial gas disk at precisely the right time. The probability calculations for this sequence suggest it's an extremely rare occurrence that might happen in fewer than 1% of planetary systems. The asteroid belt between Mars and Jupiter provides additional evidence of suspicious fine-tuning. The gravitational effects of Jupiter prevented a planet from forming in this region, instead creating a reservoir of rocky debris that occasionally impacts the inner planets. These impacts have played crucial roles in delivering water and organic compounds to Earth, while also creating extinction events that guided evolutionary development. The timing and intensity of these impacts seem almost choreographed for biological development. The late heavy bombardment ended just as conditions on Earth became suitable for complex life. Subsequent impacts occurred at intervals that eliminated evolutionary dead ends while providing opportunities for new forms of life to emerge and diversify. The Moon's formation through a giant impact event required a collision of precisely the right size, angle, and timing to create a large satellite without destroying the Earth. This impact had to occur after Earth had differentiated into core and mantle, but before life had begun, removing much of Earth's early atmosphere while leaving behind a system that would later develop the stable climate needed for complex life. The impactor that created the moon had to be exactly the right size, large enough to create a substantial satellite, but not so large as to destroy the Earth entirely. It had to strike at precisely the right angle to create the Earth-Moon system's current angular momentum while leaving both bodies intact. The probability of all these factors aligning by chance is extraordinarily small. The tidal effects created by the moon's presence have been essential for life's development in multiple ways. Tides helped marine life transition to terrestrial environments by creating intertidal zones where organisms could adapt to air exposure. The moon's gravitational influence stabilizes Earth's rotational axis, preventing the extreme climate variations that would occur if our planet wobbled chaotically like Mars. The moon's distance from Earth has been slowly increasing over geological time, but the rate of this recession seems perfectly calibrated to maintain optimal tidal effects throughout the period when complex life was developing. During the early stages of life, when tidal mixing was crucial for chemical evolution, the moon was closer and tides were stronger. As complex life evolved and extreme tides became less beneficial, the moon had receded to create more moderate tidal effects. The atmospheric evolution that created Earth's current life-supporting atmosphere required a sequence of precisely timed events that transformed a toxic early atmosphere into one that could support complex organisms. The early atmosphere contained virtually no free oxygen, which would have been lethal to early life forms, but was essential for the later evolution of complex multicellular organisms. The great oxidation event that introduced oxygen to the atmosphere occurred through biological processes, but the timing had to be perfect to avoid either oxygen poisoning of early life or insufficient oxygen for later evolutionary developments. The transition occurred gradually over hundreds of millions of years, allowing life to adapt while building up oxygen concentrations needed for complex metabolism. The regulation of atmospheric composition has continued throughout Earth's history through biogeochemical cycles that seem almost too stable to be entirely natural. The carbon cycle maintains atmospheric CO2 levels within narrow ranges through feedback mechanisms involving weathering, volcanism, and biological processes. These feedback mechanisms have prevented both runaway greenhouse effects and snowball Earth conditions that would have been fatal to life. The nitrogen cycle, phosphorus cycle, and sulfur cycle all operate with similar precision to maintain atmospheric and oceanic composition within ranges suitable for life. The mathematical modeling of these cycles reveals that they're much more stable than random geochemical processes should produce, suggesting some form of regulation or maintenance that goes beyond simple chemical equilibrium. The magnetic field that protects Earth from harmful cosmic radiation has maintained its strength and configuration over billions of years, despite the chaotic dynamics that govern planetary magnetic fields. Earth's magnetic field is generated by convection in the liquid iron core, a process that should be highly variable and unpredictable over geological timescales. Yet Earth's magnetic field has persisted throughout the time needed for complex life to evolve, with only brief interruptions during magnetic reversals. During these reversals, the field doesn't disappear entirely, but instead maintains a complex multipolar structure that continues to provide some protection from cosmic radiation. The probability of maintaining continuous magnetic protection over billions of years through random geodynamic processes is extremely low. The geological processes that have shaped Earth's surface show similar patterns of suspicious optimization for life. The rate of continental drift has been fast enough to prevent the continents from becoming geologically dead, but slow enough to allow complex ecosystems to develop and persist. The timing of major geological events like mountain building episodes and volcanic periods seems coordinated with biological needs for climate regulation and nutrient cycling. The water cycle that maintains Earth's hydrosphere operates through processes that seem precisely calibrated to support life. The amount of water on Earth's surface is exactly right, enough to create oceans that regulate climate and support marine life, but not so much that all land is submerged. the salinity of the oceans has remained within narrow ranges suitable for life despite billions of years of evaporation and mineral input from rivers and volcanic activity. The ice age cycles that have dominated Earth's recent climate history show periodicities and amplitudes that seem perfectly designed to stimulate evolutionary innovation without causing complete ecosystem collapse. These cycles are driven by variations in Earth's orbit around the Sun, but the biological and geological responses to orbital forcing show regulatory mechanisms that maintain habitability during both glacial and interglacial periods. The atmospheric composition during ice age cycles has varied within ranges that challenge life without making it impossible. Carbon dioxide levels have fluctuated between concentrations that stress plant growth and levels that would create severe greenhouse warming, but they've never exceeded the boundaries that would make Earth uninhabitable. This regulation suggests feedback mechanisms that go beyond simple physical processes. The extinction events that have punctuated Earth's biological history show patterns that seem almost designed to guide evolutionary development toward increasing complexity and intelligence. The timing of these extinctions appears coordinated with evolutionary opportunities rather than being random, catastrophic events. The Permian-Triassic extinction that eliminated over 90% of marine species occurred at precisely the time when early archosaurs were positioned to diversify and eventually give rise to dinosaurs. The later extinction that eliminated non-avian dinosaurs occurred when early mammals had developed the characteristics needed to exploit newly available ecological niches. Each major extinction event has eliminated dominant groups that might have prevented the evolution of more complex forms while preserving lineages that would later give rise to greater biological sophistication. The selectivity of these extinctions seems too precise to be explained by random environmental catastrophes. The evolutionary innovations that have driven increasing biological complexity show timing patterns that suggest coordination rather than random mutation and selection. The evolution of photosynthesis occurred when atmospheric conditions were optimal for its development. The evolution of sexual reproduction happened when genetic diversity became crucial for adaptation to changing environments. The development of multicellularity occurred simultaneously in multiple lineages, suggesting that environmental conditions had reached a threshold that made complex organization advantageous. The evolution of intelligence accelerated dramatically during periods when environmental challenges favored cognitive flexibility and social cooperation. The molecular machinery of life shows levels of sophistication that seem to exceed what should be possible through random evolutionary processes. The genetic code uses error correction mechanisms that rival the best human information technologies. The protein folding processes that create functional enzymes operate with precision that exceeds anything we can achieve with our most advanced manufacturing technologies. The metabolic pathways that power cellular processes show optimization patterns that suggest deliberate engineering rather than evolutionary accident. These pathways often use the minimum number of steps needed to convert nutrients into energy while maximizing efficiency and minimizing toxic byproducts. The mathematical analysis of metabolic networks reveals design principles that parallel those used in human-engineered systems. The cellular repair mechanisms that maintain genetic integrity and cellular function operate with remarkable precision, considering the hostile environment inside living cells. These systems can detect and correct errors that occur at the molecular level while maintaining the delicate chemical balances needed for life. The coordination required between different repair systems suggests a level of integration that's difficult to explain through undirected evolutionary processes. The developmental programs that guide the growth of complex organisms from single cells show patterns of information processing that seem more sophisticated than any human technology. These programs can coordinate the activities of trillions of cells while maintaining precise spatial and temporal control over growth, differentiation, and organ formation. The embryological development of complex organisms requires information processing capabilities that seem to exceed what should be possible using only the genetic information contained in DNA. The regulatory networks that control development show properties of programmable systems that can respond to environmental inputs while maintaining overall developmental objectives. The immune systems that protect complex organisms from disease show adaptive capabilities that rival artificial intelligence systems. These biological networks can learn to recognize new threats, remember previous encounters, and coordinate responses involving multiple types of specialized cells. The information processing requirements for these functions seem to require computational capabilities that shouldn't be possible using only biochemical processes. The nervous systems that enable complex behavior and consciousness show organizational principles that parallel those found in designed information systems. The neural networks that process sensory information, control movement, and generate thoughts operate using principles of parallel processing, distributed memory, and hierarchical control that mirror human-engineered systems. The emergence of consciousness itself remains one of the deepest mysteries in science, with no convincing explanation for how purely physical processes can give rise to subjective experience. The hard problem of consciousness suggests that awareness might involve phenomena that transcend the normal operation of physical systems. The fact that the universe has evolved beings capable of contemplating their own existence and questioning the nature of reality seems improbable beyond any reasonable expectation. The emergence of intelligence that can discover mathematical laws, create art, and ponder cosmic questions appears to serve no obvious survival function, yet has emerged on at least one planet in ways that suggest it might be an intended outcome rather than an accident. The technological limitations we encounter as we attempt to expand beyond Earth seem almost designed to contain us within our planetary boundaries, while allowing us to develop sophisticated civilizations. Every promising breakthrough in space technology encounters fundamental barriers that prevent practical implementation for interstellar exploration. The rocket equation that governs chemical propulsion creates absolute limits on payload capacity that make interstellar missions impractical regardless of technological improvements. Nuclear propulsion offers better performance, but encounters regulatory and safety obstacles that have prevented its development. More exotic propulsion concepts require energy sources or physical principles that remain beyond our technological reach. The communication delays inherent in interstellar distances create barriers to exploration that can't be overcome by any known technology. Even if we could develop spacecraft capable of reaching nearby stars, the round-trip communication time would make coordinated exploration impossible within human lifespans. The isolation created by these communication delays would make interstellar colonies essentially independent of Earth, preventing the maintenance of unified human civilization across multiple star systems. The resource requirements for interstellar exploration exceed anything that could be practically implemented using Earth-based industrial capacity. The energy needed to accelerate spacecraft to significant fractions of light speed would require global power production devoted entirely to space exploration for decades or centuries. The materials needed for radiation shielding and life support would require mining operations on scales that would transform the entire solar system. The biological challenges of interstellar travel seem almost designed to prevent human expansion beyond our local cosmic neighborhood. The radiation environment in interstellar space would require shielding so massive that spacecraft would become impractical. The psychological effects of isolation and confinement during multi-generational voyages would require social engineering on scales that have never been successfully implemented. The economic and political obstacles to sustained space exploration arise with predictable regularity just as major breakthroughs are being achieved. Funding for ambitious space programs is consistently reduced during the critical phases when sustained investment would achieve transformative capabilities. International cooperation in space exploration is disrupted by political conflicts that seem to intensify whenever significant progress is being made toward breakthrough capabilities. The environmental crises that demand immediate attention and resources occur with timing that prevents long-term focus on space expansion. Climate change, resource depletion, and ecological collapse create urgent problems that require global attention and resources, just as we're developing technologies that might enable permanent expansion beyond Earth. The social and psychological problems that accompany technological development consistently create instabilities that prevent sustained focus on long-term projects. Wars, economic crises, and political upheavals occur with timing that disrupts space programs just as they're approaching critical capabilities. The pattern of these disruptions seems almost too convenient to be entirely coincidental. The information filtering that occurs through scientific publishing, peer review, and career advancement systems ensures that research supporting the zoo hypothesis would be difficult to pursue, publish, or disseminate. The compartmentalization of scientific knowledge prevents individual researchers from accessing all the information needed to detect evidence of cosmic scale management. The funding mechanisms that support scientific research are structured to discourage investigations that might challenge fundamental assumptions about natural processes. Research proposals that suggest artificial intervention in cosmic or biological evolution would be unlikely to receive support through conventional scientific institutions. The educational systems that shape scientific understanding emphasize paradigms that discourage speculation about intentional design or artificial management of natural systems. Students are trained to think in terms of random processes and natural selection while avoiding hypotheses that might suggest purposeful intervention in cosmic or biological development. As we compile all these lines of evidence, the mathematical improbabilities multiply to levels that challenge any reasonable assessment of coincidence. The precise calibration of physical constants, the suspicious optimization of solar system architecture, the perfectly timed sequence of evolutionary innovations, the remarkable stability of Earth's environment, and the systematic barriers to space exploration all point toward the same unsettling conclusion. We appear to be living in an environment that has been carefully designed, precisely maintained, and systematically controlled in ways that are invisible to us but essential for our existence and development. Every aspect of our cosmic situation seems optimized for the emergence and development of intelligence, while preventing that intelligence from detecting or escaping the boundaries of its cosmic enclosure. The zoo hypothesis provides a framework for understanding these anomalies that is more mathematically probable than the alternatives. Rather than requiring us to accept infinite universes, impossible coincidences, or fundamental gaps in our understanding of natural processes, it suggests that we are the subjects of a cosmic experiment or preservation effort that operates according to principles and purposes that remain beyond our current comprehension. Whether this situation represents benevolent conservation, scientific study, or some other purpose entirely, the implications force us to reconsider everything we think we know about our cosmic situation and our potential for future development. The universe might be far more purposeful, far more carefully maintained, and far more mysteriously designed than we have ever dared to imagine. The quantum mechanics that governs reality at its most fundamental level reveals patterns that seem almost too convenient for conscious observers like ourselves. The measurement problem in quantum mechanics suggests that reality exists in a state of probability until conscious observation forces it to assume definite configurations. This observer effect has been demonstrated in increasingly sophisticated experiments that rule out conventional explanations. The delayed choice quantum eraser experiments show that decisions made by observers can apparently influence events that occurred in the past before the decision was made. These experiments suggest that the act of observation doesn't just reveal pre-existing reality, but actually participates in creating the reality that is observed. The implications are staggering. Conscious observers seem to play a fundamental role in determining the nature of physical reality. The quantum Zeno effect demonstrates that frequent observation can freeze quantum systems in particular states, preventing them from evolving according to their natural dynamics. This suggests that consciousness might have the ability to stabilize reality through the act of observation, maintaining consistent physical laws and stable environmental conditions through the ongoing process of measurement and awareness. The many worlds interpretation of quantum mechanics proposes that all possible quantum states exist simultaneously until observation selects one particular outcome. If this interpretation is correct, then conscious observers are continuously selecting which version of reality they experience from an infinite array of possibilities. This process could be seen as a form of reality maintenance that requires conscious participation to function properly. The role of information in quantum mechanics has led some physicists to propose that reality is fundamentally informational rather than material. The IT from bit hypothesis suggests that all physical phenomena emerge from information processing rather than existing as independent material objects. If reality is indeed informational, then it might be much easier to design and maintain than we typically assume. The holographic principle in physics suggests that all the information contained in a volume of space can be encoded on its boundary. This implies that what we experience as three-dimensional reality might actually be a projection from information encoded on a two-dimensional surface. The holographic nature of reality would make it far easier for advanced intelligences to create and maintain simulated environments that are indistinguishable from natural reality. The anthropic coincidences that enable our existence extend far beyond the fundamental constants of physics to include the specific properties of atoms, molecules, and chemical processes that make complex chemistry possible. The carbon atom has exactly the right properties to form the complex molecules needed for life. It can form 4 bonds, create stable chains and rings, and participate in the intricate chemical networks that characterize living systems. Water shows properties that seem specifically designed for life. Its density maximum at 4 degrees Celsius prevents bodies of water from freezing solid from the bottom up, creating insulated environments where life can survive during ice ages. Its high specific heat capacity moderates temperature fluctuations that would otherwise be lethal to biological processes. Its solvent properties enable the complex chemical reactions that characterize metabolism. The chemical elements that are essential for life, hydrogen, carbon, nitrogen, oxygen, phosphorus, and sulfur, have atomic properties that enable them to form the complex molecules needed for biological processes. The precise balance between the strengths of different types of chemical bonds allows biological molecules to be stable enough to maintain their structure, but flexible enough to participate in dynamic chemical processes. The periodic table itself shows patterns of organization that seem almost designed to support complex chemistry. The electron configurations that determine chemical properties follow mathematical patterns that create systematic variations in atomic behavior. The existence of this underlying mathematical order enables the prediction and manipulation of chemical processes that would be impossible in a randomly organized system. The biochemical processes that power life show optimization patterns that parallel those found in engineered systems. Metabolic pathways often use the minimum number of steps needed to convert raw materials into useful products while maximizing efficiency and minimizing waste. The enzymes that catalyze these processes show specificities and reaction rates that seem optimized for their biological functions. The genetic code that translates DNA sequences into proteins shows error-correcting properties that minimize the impact of mutations on biological function. The code is organized so that many mutations result in no change in the protein product, while others produce only conservative changes that don't significantly alter protein function. This error tolerance seems too sophisticated to have emerged through random processes. The protein folding problem reveals another layer of biological sophistication that seems to exceed what should be possible through natural selection. Proteins must fold into precisely defined three-dimensional structures to function properly, and the number of possible folding configurations is astronomically large. Yet proteins consistently fold into their correct structures within seconds or minutes, a process that should take longer than the age of the universe if it occurred through random trial and error. The cellular machinery that synthesizes proteins operates with precision that exceeds any human manufacturing technology. Ribosomes can translate genetic information into protein sequences with error rates lower than 1 mistake per 10,000 amino acids, while operating at speeds that produce hundreds of proteins per minute. This combination of speed and accuracy requires quality control mechanisms that rival the most sophisticated human industrial processes. The DNA replication process that copies genetic information during cell division operates with similar precision and speed. The molecular machines that unwind DNA, synthesize new strands, and proofread the results work together in a coordinated process that maintains genetic fidelity across billions of years of evolution. The error rate in DNA replication is so low that it enables the stable inheritance of complex genetic information across countless generations. The cellular repair systems that maintain genetic integrity operate continuously to correct damage from radiation, chemical exposure, and normal metabolic processes. These systems can recognize dozens of different types of DNA damage and repair each type using specialized molecular mechanisms. The coordination between different repair systems ensures that cells can maintain genetic stability in the face of constant environmental challenges. The developmental programs that guide the growth of complex organisms show information processing capabilities that seem to exceed what should be possible using biochemical processes alone. A single fertilized egg contains the information needed to coordinate the growth and differentiation of trillions of cells into a functioning organism with hundreds of different cell types organized into complex organs and systems. The regulatory networks that control gene expression during development show properties of programmable systems that can respond to environmental inputs while maintaining precise control over cellular behavior. These networks can process multiple inputs simultaneously, store information about previous states, and generate outputs that control complex cellular behaviors. The computational capabilities of these biological systems rival those of sophisticated artificial intelligence systems. The neural networks that enable complex behavior and consciousness show organizational principles that seem specifically designed for information processing. The human brain contains approximately 86 billion neurons connected by trillions of synapses, creating a network with computational capabilities that exceed any artificial system yet created. The hierarchical organization of neural processing, from individual neurons to local circuits to brain regions to global networks, enables the integration of information across multiple scales and timescales. This organization allows the brain to process sensory information, store memories, generate plans, and produce conscious experiences through mechanisms that remain largely mysterious despite decades of intensive research. The plasticity of neural systems allows the brain to reorganize itself in response to experience, injury, or changing environmental demands. This adaptive capability enables learning, recovery from brain damage, and the development of new skills throughout life. The mechanisms that control neural plasticity seem optimized to maximize learning while maintaining stable memory storage and consistent behavioral patterns. The consciousness that emerges from neural activity represents perhaps the most mysterious aspect of our existence. The subjective experience of awareness, the sense of being a unified self, experiencing a coherent world, and the ability to contemplate abstract concepts like meaning and purpose seem to transcend the purely physical processes occurring in the brain. The hard problem of consciousness, explaining how subjective experience arises from objective physical processes, remains unsolved despite extensive research. The qualitative nature of conscious experience seems fundamentally different from the quantitative properties of physical systems, suggesting that consciousness might involve principles that go beyond conventional physics. The binding problem in consciousness research asks how the brain integrates information from multiple sources into unified conscious experiences. When you look at a red ball, your brain processes information about color, shape, motion, and texture in different regions, yet you experience a single integrated perception of a red ball. The mechanisms that create this unified experience from distributed neural activity remain largely unknown. The global workspace theory suggests that consciousness arises when information becomes globally accessible throughout the brain, enabling different brain regions to share information and coordinate their activities. This theory implies that consciousness serves as a biological information integration system that enables flexible, adaptive behavior in complex environments. The sociological patterns that characterize human civilization show organizational principles that seem designed to prevent sustained focus on space exploration and cosmic expansion. Human societies consistently develop internal conflicts, resource competition, and political instabilities that prevent long-term cooperation on projects that might enable escape from planetary boundaries. The economic systems that drive technological development consistently prioritize short-term profits over long-term investments in space exploration. The market mechanisms that allocate resources are structured in ways that make sustained, multi-generational projects economically impractical. The financial incentives that motivate innovation systematically favor developments that provide immediate returns rather than breakthrough capabilities that might transform human cosmic potential. The political systems that could organize major space initiatives are designed with election cycles and term limits that prevent sustained commitment to long-term projects. The democratic processes that determine funding priorities ensure that space exploration must compete with immediate social needs for limited resources. The international relations that could enable global cooperation in space exploration are consistently disrupted by conflicts that prevent sustained collaboration. The military-industrial complexes that possess the technological capabilities needed for advanced space exploration are primarily focused on terrestrial applications that serve national interests rather than species-wide expansion capabilities. The classification systems that protect sensitive technologies often prevent the international cooperation that would be needed for major space initiatives. The environmental problems that demand immediate attention consistently arise just as space technologies are approaching breakthrough capabilities. Climate change, resource depletion, and ecological collapse create urgent crises that require massive resource investments and global attention, preventing sustained focus on space expansion. The timing of these environmental challenges seems almost coordinated with human technological development. The psychological factors that influence human behavior seem systematically biased against sustained space exploration. Humans show strong preferences for familiar environments, immediate rewards, and local social connections that make long-term space missions psychologically challenging. The cognitive biases that shape human decision-making consistently favor short-term thinking over long-term planning. The cultural values that influence social priorities emphasize terrestrial concerns over cosmic expansion. Religious and philosophical systems typically focus on earthly existence and human relationships, rather than encouraging exploration of the wider universe. The educational systems that shape intellectual development rarely emphasize the importance of space exploration or cosmic perspective. The media systems that shape public opinion consistently portray space exploration as expensive, risky, and less important than immediate social needs. The entertainment industries that influence cultural values rarely present positive visions of human expansion into space. The communication technologies that could build support for space exploration are primarily used for terrestrial social networking and consumption. The technological development patterns that characterize human civilization show systematic limitations that prevent breakthrough capabilities in space exploration. Every promising advancement in propulsion, life support, or space habitation encounters fundamental barriers that prevent practical implementation. The pattern of these limitations seems too consistent to be entirely coincidental. The energy sources available for space exploration remain limited to chemical, nuclear, and solar technologies that provide insufficient power for interstellar missions. More exotic energy sources like antimatter, fusion, or zero-point energy consistently encounter technical obstacles that prevent practical development. The theoretical possibilities for advanced propulsion remain tantalizing, but practically unachievable. The materials science advances needed for space exploration face fundamental limits imposed by atomic structure and chemical bonding. The strongest possible materials are limited by the properties of atoms and molecules, preventing the construction of structures large enough for interstellar missions. The manufacturing capabilities needed for space exploration require precision and scale that remain beyond current technological reach. The life support systems needed for long-term space missions require closed-loop ecological systems that have never been successfully implemented on the scales needed for space exploration. The psychological support systems needed for multi-generational space missions would require social engineering capabilities that exceed anything ever attempted in human society. The communication systems needed to maintain contact with interstellar missions face fundamental limits imposed by the speed of light and signal degradation over cosmic distances. The round-trip communication times to even the nearest stars would make coordinated exploration impossible within human lifespans. The isolation created by these communication delays would make interstellar colonies essentially independent of Earth. The navigation systems needed for interstellar missions would require positional accuracy over distances and timescales that exceed current capabilities by many orders of magnitude. The gravitational influences that affect spacecraft trajectories over interstellar distances include countless bodies whose positions and masses are unknown. The computational requirements for accurate navigation over such distances and timescales exceed current technological capabilities. The radiation shielding needed for interstellar missions would require materials and configurations that make spacecraft prohibitively massive. The cosmic ray environment in interstellar space would deliver lethal doses of radiation to unprotected humans over the timescales needed for interstellar missions. The electromagnetic interference from cosmic radiation would disrupt electronic systems essential for spacecraft operation. The scientific discoveries that have revealed these limitations seem to arise at precisely the times when space exploration capabilities are approaching breakthrough levels. The discovery of cosmic radiation occurred just as space exploration was beginning. The realization of interstellar distances and communication delays became clear just as radio technology was developing. The understanding of energy requirements for interstellar travel emerged just as nuclear technology was being developed. The pattern of scientific discoveries seems almost designed to reveal fundamental barriers to space exploration, just as technological capabilities approach the levels where these barriers become relevant. Each new understanding of cosmic reality reveals additional obstacles to expansion beyond Earth that weren't apparent when space exploration began. The institutional structures that govern scientific research and technological development are organized in ways that prevent sustained focus on breakthrough space technologies. The peer review processes that determine research funding are conservative and risk-averse, discouraging investigations of exotic propulsion concepts or advanced life support systems. The career incentives that motivate researchers favor incremental advances over revolutionary breakthroughs. The patent systems that protect intellectual property create barriers to the international cooperation that would be needed for major space exploration projects. The commercial interests that drive technological development are primarily focused on terrestrial applications rather than space exploration capabilities. The military secrecy that surrounds advanced technologies often prevents the open research collaboration needed for breakthrough developments. The educational systems that train scientists and engineers rarely emphasize space exploration as a primary career focus. The funding mechanisms that support advanced research consistently underfund space-related projects compared to terrestrial applications. The infrastructure needed for advanced space research requires investments that exceed what individual nations or institutions can practically support. As we examine all these systematic barriers, limitations, and suspicious coincidences together, the pattern becomes overwhelming. Every aspect of our situation, from the fundamental constants of physics to the specific details of human psychology, seems calibrated to enable the development of intelligence while preventing that intelligence from detecting or escaping the boundaries of its cosmic environment. The mathematical improbabilities involved in all these factors aligning by pure chance are so remote that they approach impossibility. The alternative explanations, infinite universes, extraordinary luck, or fundamental gaps in our understanding, require us to accept premises that are at least as extraordinary as the zoo hypothesis itself. The possibility that we are living in a carefully maintained cosmic preserve, designed and monitored by intelligences whose capabilities and motivations transcend our current understanding, provides a coherent explanation for all these anomalies. We might be the subjects of the most sophisticated conservation effort ever attempted, protected, and nurtured by cosmic gardeners who see intelligence as the most precious phenomenon in the universe. Whether this situation represents benevolent protection, scientific study, aesthetic appreciation, or purposes we cannot imagine, the implications challenge everything we think we know about reality, consciousness, and our potential for cosmic expansion. The zoo hypothesis forces us to confront the possibility that we are not the independent explorers of a natural universe that we believe ourselves to be, but rather the carefully tended inhabitants of an artificial paradise whose boundaries we are only beginning to perceive. The question of whether we are inside an alien zoo may be the most important question our species has ever confronted, because the answer determines not just our understanding of the past, but our possibilities for the future. If we are indeed contained within invisible boundaries, then discovering the nature of our containment might be the first step toward transcending it, or it might be the realization that transcendence is neither possible nor necessary for a meaningful existence within our cosmic terrarium. The historical patterns of human technological development reveal cycles that seem almost designed to maintain civilization within sustainable boundaries while preventing breakthrough capabilities that might enable cosmic expansion. Each major technological revolution has brought transformative benefits for human society while simultaneously creating new limitations and dependencies that constrain our cosmic potential. The agricultural revolution enabled the development of complex civilizations, but also created dependencies on specific geographic locations and climate conditions that made interplanetary colonization more difficult. Hunter-gatherer societies were naturally adapted for mobility and resource independence, but agricultural societies became tied to specific territories and environmental conditions that don't exist beyond Earth. The Industrial Revolution provided the technological foundation for space exploration, but also created environmental problems and resource dependencies that require constant attention and management. The fossil fuel technologies that enabled industrial development are inherently limited and environmentally destructive, creating urgent problems that demand resources and attention that might otherwise support space exploration. The nuclear revolution provided both the energy sources needed for advanced space missions and the weapons capabilities that threaten human survival. The same technologies that could power interstellar exploration have created geopolitical tensions and existential risks that prevent sustained international cooperation in space development. The information revolution has provided the computational capabilities needed for complex space missions while also creating new forms of social fragmentation and psychological dependency that make long-term space exploration psychologically challenging. The digital technologies that could enable space exploration have also created addictive virtual environments that reduce interest in physical exploration. Each technological revolution has followed a similar pattern: initial promises of liberation and expansion, followed by the emergence of new constraints and dependencies that limit the revolutionary potential. The pattern suggests that technological development might be guided by invisible influences that ensure each advance brings both benefits and new forms of containment. The demographic patterns that characterize human population dynamics show cycles that seem calibrated to prevent both extinction and exponential expansion beyond planetary boundaries. Human population growth has accelerated during periods when resources were abundant, but has been consistently checked by wars, diseases, and environmental constraints that prevent unlimited expansion. The demographic transition that accompanies technological development consistently reduces birth rates, just as societies develop the capabilities that might enable space colonization. Advanced technological societies show fertility rates below replacement levels, suggesting that technological development itself creates psychological or social factors that discourage reproduction and expansion. The urbanization patterns that accompany technological development consistently concentrate human populations in dense metropolitan areas that are psychologically and technologically dependent on complex infrastructure systems. These urban environments create lifestyle preferences and psychological dependencies that make the isolation and simplicity of space exploration psychologically unappealing. The resource consumption patterns that characterize advanced technological societies create dependencies on complex global supply chains and environmental systems that make self-sufficient space colonies technically and economically impractical. The lifestyle expectations of technologically advanced populations require resource flows and waste disposal systems that cannot be replicated in space environments. The linguistic evidence reveals patterns in human communication that seem designed to enable sophisticated cultural development while preventing the kinds of global coordination that might enable sustained space exploration efforts. The diversity of human languages creates barriers to international cooperation that are strong enough to prevent unified space programs, but not so strong as to prevent limited cultural and technological exchange. The rate of language change and diversification seems calibrated to maintain cultural diversity while preventing the emergence of truly global communication systems. Translation technologies advance rapidly enough to enable basic international cooperation, but remain imperfect enough to prevent the deep cultural integration that would be needed for unified cosmic expansion efforts. The evolution of communication technologies follows patterns that seem designed to enhance local social connections while creating new barriers to the kinds of long-term, large-scale coordination needed for interstellar exploration. Social media technologies create addictive, local social networks that reduce interest in distant exploration and long-term planning. The information overload created by advanced communication systems consistently overwhelms human cognitive capabilities, just as the complexity of space exploration projects reaches levels that require sustained public attention and support. The attention spans and focus capabilities needed for long-term space projects are systematically undermined by information technologies that provide immediate gratification and constant distraction. The educational systems that shape human intellectual development show patterns that seem designed to produce technically capable individuals while preventing the kinds of holistic, long-term thinking that would be needed to organize sustained cosmic expansion efforts. Educational specialization creates experts in narrow technical fields, but discourages the interdisciplinary thinking needed for complex space projects. The career incentive structures that motivate educational and professional development consistently reward specialization and short-term achievements over the kinds of long-term, interdisciplinary thinking that would be needed for breakthrough space technologies. The peer review systems that govern academic and professional advancement are conservative and risk-averse, discouraging the kinds of revolutionary thinking that might enable cosmic expansion. The institutional memory systems that preserve human knowledge are designed to maintain technical capabilities over decades, but not over the centuries or millennia that would be needed for sustained interstellar exploration projects. The documentation systems and knowledge transfer mechanisms that preserve technical knowledge consistently fail over the timescales needed for multi-generational space projects. The philosophical and religious systems that shape human values and priorities consistently emphasize terrestrial concerns over cosmic exploration. Religious traditions typically focus on earthly existence, social relationships, and spiritual development, rather than encouraging physical exploration of the wider universe. The moral frameworks that guide human decision-making rarely include cosmic expansion as a fundamental ethical imperative. The aesthetic preferences that influence human cultural development show systematic biases toward natural Earth environments rather than the artificial environments that would characterize space habitats. Human art, literature, and entertainment consistently celebrate natural landscapes, biological diversity, and traditional social relationships rather than the technological environments and expanded social organizations that would be needed for cosmic expansion. The psychological reward systems that motivate human behavior are calibrated to provide satisfaction from terrestrial activities and social relationships rather than from the kinds of long-term, abstract achievements that would characterize successful space exploration. The dopamine pathways that generate pleasure and motivation respond more strongly to immediate social and sensory rewards than to the delayed gratifications associated with space exploration. The social bonding mechanisms that create human communities consistently emphasize local relationships and immediate social networks over the kinds of extended, abstract loyalties that would be needed for multi-generational space projects. The oxytocin and other neurochemical systems that create social cohesion are optimized for face-to-face relationships in small communities rather than the kinds of large-scale, technologically mediated social organization needed for space exploration. The risk assessment mechanisms that govern human decision-making show systematic biases that make space exploration appear more dangerous and less rewarding than terrestrial alternatives. The cognitive biases that shape human judgment consistently overestimate the risks of space exploration while underestimating the long-term risks of remaining confined to Earth. The temporal discounting that affects human planning and decision-making makes long-term space exploration projects psychologically unappealing compared to immediate terrestrial alternatives. The neural mechanisms that evaluate future rewards consistently undervalue long-term benefits compared to immediate gratifications, making sustained investment in space exploration difficult to maintain. The atmospheric physics that governs Earth's climate system operates according to principles that seem almost designed to maintain habitability while preventing the development of technologies that might enable atmospheric manipulation or artificial atmosphere creation. The greenhouse effect maintains Earth's temperature within habitable ranges but operates through mechanisms that are difficult to control or replicate artificially. The atmospheric composition that supports human life is maintained through biogeochemical cycles that are too complex for humans to fully understand or replicate in artificial environments. The oxygen cycle, nitrogen cycle, and carbon cycle all operate through biological and geological processes that require planetary-scale ecosystems to maintain. The atmospheric dynamics that create weather patterns and climate systems operate through nonlinear processes that are chaotic and unpredictable over the timescales needed for reliable environmental control. The computational requirements for accurate weather prediction exceed current technological capabilities even for short-term forecasts, making long-term climate control effectively impossible. The atmospheric chemistry that enables breathable air involves trace gases and complex molecular interactions that are essential for human health but poorly understood and difficult to maintain artificially. The atmospheric pressure, humidity, and gas composition that humans require for survival fall within narrow ranges that are difficult to maintain in artificial environments. The oceanic systems that regulate Earth's climate and atmospheric composition operate through mechanisms that are far too complex for human technology to replicate or control. The thermohaline circulation that distributes heat around the planet involves currents and temperature gradients that span the entire globe and operate over timescales of centuries to millennia. The marine ecosystems that produce much of Earth's oxygen and absorb much of its carbon dioxide involve biological communities with millions of species interacting through food webs and biogeochemical cycles that are far too complex for human science to fully understand or artificially maintain. The oceanic chemistry that maintains the pH and mineral content needed for marine life operates through buffer systems and equilibrium processes that involve the entire ocean volume and interact with atmospheric and geological systems on planetary scales. The precision required to maintain these chemical balances artificially would exceed any conceivable human technological capability. The geological processes that maintain Earth's habitability operate through mechanisms that seem almost designed to provide long-term stability while preventing human technological control over planetary systems. The plate tectonic processes that recycle crustal materials and regulate volcanic activity operate through mechanisms that are far too large and slow for human influence. The volcanic activity that releases gases and minerals essential for atmospheric and oceanic chemistry operates through processes that are unpredictable and uncontrollable by human technology. The timing and intensity of volcanic eruptions affect global climate and atmospheric composition, but cannot be predicted or controlled with current or foreseeable technology. The seismic activity that accompanies geological processes creates natural hazards that consistently disrupt human technological systems, but rarely cause permanent damage to planetary habitability. The frequency and intensity of earthquakes seem calibrated to prevent overconfidence in technological control while maintaining overall geological stability. The mineral cycles that provide essential elements for biological systems operate through weathering, erosion, and sedimentation processes that span millions of years and involve the entire planetary surface. The availability of phosphorus, sulfur, and trace elements needed for life depends on geological processes that are completely beyond human control. The magnetic field generation that protects Earth from cosmic radiation operates through geodynamic processes in the planetary core that are completely inaccessible to human influence. The magnetic field reversals that occasionally occur seem to be timed to avoid permanent damage to the biosphere, but serve as reminders of humanity's dependence on planetary systems beyond our control. The solar system architecture that enables Earth's habitability involves orbital dynamics and gravitational interactions that operate according to principles that prevent human technological intervention. The gravitational influences of Jupiter and other planets that protect Earth from asteroid impacts operate through celestial mechanics that are completely beyond human influence. The asteroid and comet populations that pose impact threats to Earth follow orbital patterns that create predictable hazards, but also provide resources that might eventually enable space development. The timing and distribution of impact hazards seem calibrated to motivate space technology development, while preventing both complacency and despair about humanity's cosmic situation. The solar activity cycles that affect Earth's climate and technology operate through stellar processes that are completely beyond human influence, but seem to be calibrated to avoid permanent damage to terrestrial civilization. The solar maximum and minimum cycles create technological disruptions that serve as reminders of humanity's dependence on cosmic systems while maintaining overall habitability. The cosmic ray environment that affects both human health and electronic systems in space creates barriers to space exploration that increase with distance from Earth's protective magnetosphere. The radiation levels in interplanetary space require shielding that makes spacecraft prohibitively massive, while the radiation in interstellar space would be lethal to unprotected humans over mission timescales. The interstellar medium that spacecraft would encounter during interstellar missions contains dust and gas that would create erosion and contamination problems over the timescales needed for interstellar travel. The density of interstellar matter seems low enough to allow theoretical interstellar travel, but high enough to create practical obstacles that make such travel extremely difficult. The galactic structure that determines the distribution of stars and planets creates distances between potentially habitable systems that are just large enough to make interstellar travel extremely difficult, but not so large as to make it obviously impossible. The nearest potentially habitable exoplanets are far enough away to require technological capabilities that remain beyond current reach, but close enough to remain tantalizing possibilities. The cosmic expansion that governs the large-scale structure of the universe creates distances between galaxies that increase over time ensuring that intergalactic travel becomes increasingly difficult as cosmic time progresses. The rate of cosmic expansion seems calibrated to maintain the possibility of intragalactic exploration while preventing expansion beyond our local galactic group. The dark energy that drives cosmic expansion operates through mechanisms that are completely mysterious but seem to be precisely calibrated to maintain cosmic structure while preventing unlimited expansion. The cosmological constant that governs dark energy has exactly the value needed to allow galaxy formation while ensuring that cosmic expansion will continue indefinitely. The dark matter that provides the gravitational scaffolding for cosmic structure operates through interactions that remain completely mysterious despite decades of investigation. The properties of dark matter seem precisely calibrated to enable galaxy and star formation while remaining essentially invisible to human detection methods. The fundamental forces that govern all physical interactions operate according to principles that seem designed to enable complex structures like atoms, stars, and planets while preventing the kinds of exotic physics that might enable faster-than-light travel or unlimited energy generation. The strength ratios between different forces create a universe that supports complexity but maintains absolute limits on technological capabilities. The conservation laws that govern energy, momentum, and other physical quantities create absolute constraints on technological possibilities that cannot be circumvented by any conceivable technology. These conservation laws enable the stability and predictability needed for technological civilization while preventing the kinds of breakthrough capabilities that might enable unlimited cosmic expansion. The thermodynamic principles that govern energy flow and entropy generation create fundamental limits on the efficiency of any technological process. The second law of thermodynamics ensures that all technological systems require continuous energy input and generate waste heat, preventing the development of perfectly efficient closed-loop systems that might enable unlimited expansion. The speed of light creates absolute limits on information transfer and coordination that make large-scale space exploration practically impossible regardless of technological capabilities. The communication delays inherent in interstellar distances prevent the kinds of real-time coordination that would be needed for sustained exploration and colonization efforts. The quantum mechanical principles that govern matter and energy at fundamental scales create uncertainties and limitations that prevent perfect measurement and control of physical systems. The Heisenberg uncertainty principle ensures that perfect knowledge and control of physical systems is fundamentally impossible, limiting the precision of any technological system. As we survey this vast web of constraints, limitations, and suspicious coincidences, the cumulative evidence becomes overwhelming. Every aspect of physical reality, from quantum mechanics to cosmic structure, seems calibrated to enable the development of intelligence and technological civilization while preventing that intelligence from escaping planetary boundaries or detecting artificial management of its environment. The mathematical probability that all these factors could align by pure chance approaches zero. The precision required for each individual factor is extraordinary, and the probability that all of them could be simultaneously calibrated to maintain a cosmic zoo environment defies any reasonable expectation of coincidence. The alternative explanations, infinite universes, impossible luck, or fundamental gaps in our scientific understanding, all require premises that are at least as extraordinary as the zoo hypothesis itself. The multiverse theories that might explain fine-tuning require accepting the existence of infinite unobservable realities. The appeals to ignorance require believing that future discoveries will somehow explain away all these suspicious patterns. The zoo hypothesis provides a more economical explanation that accounts for all the observed patterns with a single, coherent framework. We appear to be living in an artificially maintained environment, carefully designed to enable the development of intelligence, while preventing that intelligence from detecting or transcending its cosmic boundaries. The purpose of this cosmic preserve remains mysterious, but the evidence for its existence seems undeniable when examined objectively. We may be the subjects of the most sophisticated conservation effort ever attempted, protected and nurtured by cosmic gardeners whose capabilities and motivations transcend our current understanding. Whether this represents benevolent protection, scientific study, aesthetic appreciation, or purposes beyond our imagination, the implications challenge everything we believe about reality, consciousness, and human potential. The possibility that we are inhabitants of an alien zoo forces us to reconsider not just our cosmic situation, but the very nature of existence itself. The greatest question facing our species may not be whether we are alone in the universe, but whether we are truly free within it. The answer to that question will determine not just our understanding of the past and present, but our possibilities for a future that may be far more constrained or far more magnificent than we have ever dared to imagine. The archaeological anomalies that pepper human history reveal patterns of advanced knowledge that seem to appear and disappear according to cycles that might reflect periodic intervention or guidance by external intelligences. Ancient civilizations consistently demonstrated astronomical knowledge that exceeded what should have been possible with their supposed technological capabilities, yet this knowledge rarely led to sustained technological advancement that might threaten cosmic boundaries. The astronomical alignments found in megalithic structures around the world demonstrate precise knowledge of celestial mechanics, precession cycles, and mathematical relationships that required centuries of careful observation and calculation to determine. The builders of Stonehenge, the pyramids of Giza, and countless other ancient monuments possessed astronomical knowledge that rivals modern understanding, yet they never developed the industrial technologies that might have enabled space exploration. The mathematical knowledge embedded in ancient architecture reveals understanding of geometric principles, proportional relationships, and engineering techniques that seem to exceed what should have been possible without advanced computational tools. The precise measurements and complex calculations required for these structures suggest access to mathematical knowledge that was somehow available without the accumulated scientific tradition that modern mathematics required to develop. The metallurgical achievements of ancient civilizations show evidence of techniques and alloys that modern science has only recently understood or rediscovered. The Damascus steel of medieval times, the corrosion-resistant iron of the Delhi pillar, and the precision bronze work of ancient artisans all demonstrate technical capabilities that seem anachronistic for their time periods. Yet these advanced capabilities never coalesced into sustained technological traditions that might have led to industrial development and space exploration. Each civilization that demonstrated advanced knowledge eventually declined or was destroyed, and the knowledge was lost or reduced to fragmentary traditions that prevented technological accumulation across generations. The pattern suggests that advanced knowledge might have been periodically introduced into human cultures by external sources, but in ways that enabled local achievements without threatening the broader containment of human civilization within planetary boundaries. The knowledge was sufficient to inspire magnificent cultural achievements, but insufficient to enable technological transcendence. The linguistic anomalies found in ancient texts and traditions reveal knowledge of cosmic concepts and technical principles that seem to exceed what should have been available to pre-scientific cultures. Ancient Sanskrit texts describe flying machines, atomic theory, and cosmic timescales that parallel modern scientific understanding, yet these descriptions are embedded in mythological contexts that prevented their development into practical technologies. The biblical and religious traditions of various cultures contain descriptions of cosmic phenomena, advanced technologies, and interaction with non-human intelligences that are consistent with advanced knowledge, but presented in theological frameworks that discouraged scientific investigation. The visions described by religious figures often include accurate descriptions of cosmic structure and advanced technologies, but embedded in spiritual contexts that prevented technological development. The mythological traditions of cultures around the world consistently describe interactions with advanced beings who provided knowledge, tools, and guidance to early human civilizations. These traditions are remarkably consistent across geographically separated cultures that had no contact with each other, suggesting either common sources of advanced contact or deeply embedded racial memories of such contact. The cargo cult phenomena observed in modern anthropology demonstrate how contact with advanced technologies can create religious and cultural responses that preserve memory of advanced capabilities while preventing practical technological development. Indigenous cultures that encountered modern technology often created ritualistic imitations of the technology without understanding or developing its underlying principles. This pattern might explain how advanced knowledge could be introduced into human cultures in ways that inspired cultural and intellectual development without enabling technological advancement that might threaten cosmic containment. The knowledge would be preserved in mythological and religious traditions that maintained cultural memory while preventing practical application. The genetic anomalies found in human DNA reveal patterns that seem inconsistent with gradual evolutionary development through natural selection alone. The human genome contains sequences that appear to be highly optimized for specific functions, but show no clear evolutionary pathway from simpler precursors in related species. The regulatory sequences that control gene expression in humans show patterns of organization that parallel those found in engineered systems, with modular structures, error-checking mechanisms, and redundant backup systems that seem more sophisticated than what should emerge through random mutation and selection. These sequences enable the precise developmental programs that guide human embryological development, but require information content that exceeds what should be possible through undirected evolutionary processes. The junk DNA sequences that make up large portions of the human genome are increasingly being found to have regulatory and structural functions that were previously unrecognized. Many of these sequences show patterns of organization that suggest they might serve as information storage or processing systems that operate according to principles that current molecular biology doesn't understand. The endogenous retroviruses embedded in human DNA show patterns that suggest they might serve functions related to neural development and immune regulation, rather than being simply parasitic genetic elements. These sequences appear to play important roles in human brain development and consciousness that distinguish humans from other primates, suggesting they might represent modifications that were specifically introduced to enhance human cognitive capabilities. The mitochondrial DNA that exists in human cells shows patterns of inheritance and mutation that are consistent with a severe population bottleneck in recent human evolutionary history, but the genetic diversity patterns suggest this bottleneck might have involved artificial selection or genetic modification rather than simple population reduction through natural catastrophes. The chromosomal anomalies that distinguish humans from other primates include structural changes that appear to have occurred simultaneously rather than through gradual evolutionary modification. Human chromosome 2 appears to be the result of a fusion event that combined two separate chromosomes, but this fusion shows characteristics that suggest it might have been artificially induced rather than occurring through natural processes. The epigenetic mechanisms that regulate gene expression in humans show patterns of inheritance that enable rapid adaptation to environmental changes, but also create dependencies on cultural and technological systems for optimal function. These mechanisms allow human biology to adapt to artificial environments, but make humans increasingly dependent on technological support systems. The immunological profile of modern humans shows patterns that suggest adaptation to pathogen loads and environmental stresses that are characteristic of high-density agricultural societies rather than small hunter-gatherer populations. The genetic variants that provide disease resistance in modern human populations appear to have been selected for conditions that didn't exist when these variants supposedly evolved. The neurological development patterns that characterize human brain growth show requirements for specific types of environmental stimulation and social interaction that assume exposure to complex cultural environments. Human children who are deprived of appropriate cultural stimulation during critical developmental periods suffer permanent cognitive and social deficits that suggest human neurology is specifically adapted for cultural rather than natural environments. The psychological profiles that characterize human personality and behavior show patterns that seem optimized for functioning in complex technological societies rather than simple hunter-gatherer groups. The cognitive capabilities, emotional responses, and social behaviors that humans exhibit are better suited to urban technological environments than to the natural environments where humans supposedly evolved. The sensory capabilities that humans possess show patterns of optimization for artificial environments rather than natural settings. Human vision is optimized for the wavelengths produced by fire and artificial lighting rather than natural sunlight. Human hearing is optimized for the frequency ranges used in human speech and music rather than for detecting natural sounds that would be important for survival. The sleep patterns and circadian rhythms that govern human physiology are calibrated for environments with artificial lighting and complex scheduling demands rather than natural day-night cycles. Human sleep architecture includes stages that seem specifically designed for processing cultural information and maintaining social relationships rather than simple biological recovery. The nutritional requirements that characterize human metabolism are optimized for processed foods and cooked diets rather than the raw foods that would have been available in natural environments. Human digestive systems have lost many of the capabilities that other primates use to process raw plant materials, making humans dependent on food processing technologies for basic survival. The reproductive patterns that characterize human sexuality and parenting show adaptations for complex social environments rather than simple biological reproduction. Human reproductive behavior includes features like concealed ovulation, extended childhood, and intensive parental care that make sense in technological societies but would be disadvantageous in natural environments. The aging patterns that characterize human longevity show extended post-reproductive lifespans that serve functions related to cultural knowledge, preservation, and transmission rather than biological fitness. The cognitive capabilities that are preserved during human aging are specifically those that are most important for cultural transmission, while capabilities related to physical survival decline more rapidly. The technological intuitions that humans exhibit show understanding of mechanical principles, mathematical relationships, and design concepts that seem to exceed what should be available through direct experience with natural environments. Human children demonstrate intuitive understanding of physics, mathematics, and engineering concepts that enable rapid mastery of complex technologies, but serve no obvious function in natural settings. The artistic capabilities that characterize human creativity show patterns of aesthetic preference and symbolic representation that seem specifically adapted for cultural communication rather than natural environmental navigation. Human artistic production demonstrates understanding of proportion, harmony, and symbolic meaning that enables sophisticated cultural expression but provides no obvious survival advantages. The musical capabilities that humans exhibit show neural specializations for processing complex acoustic patterns that are found in human musical traditions but not in natural soundscapes. Human musical abilities include perfect pitch recognition, rhythmic coordination, and harmonic understanding that enable sophisticated musical communication but serve no clear biological functions. The mathematical capabilities that humans possess include intuitive understanding of numerical concepts, geometric relationships, and logical principles that enable rapid mastery of abstract mathematical systems but exceed what should be necessary for survival in natural environments. Human mathematical intuitions seem specifically designed for technological and scientific applications rather than natural problem solving. The linguistic capabilities that characterize human communication show neural specializations for processing grammatical structures, semantic relationships, and symbolic representations that enable sophisticated cultural transmission but exceed what should be necessary for basic social coordination. Human language capabilities seem specifically designed for maintaining complex cultural knowledge systems rather than simple communication needs. The social capabilities that humans exhibit include understanding of complex hierarchical relationships, institutional structures, and collective decision-making processes that enable coordination in large technological societies but exceed what should be necessary for small hunter-gatherer groups. Human social cognition seems specifically adapted for navigating complex institutional environments rather than simple kin-based societies. The moral reasoning capabilities that characterize human ethical thinking include understanding of abstract principles like justice, rights, and obligations that enable coordination in large anonymous societies but exceed what should be necessary for maintaining cooperation in small face-to-face groups. Human moral psychology seems specifically adapted for technological societies rather than traditional social environments. The temporal reasoning capabilities that humans possess include understanding of historical causation, future consequences, and intergenerational effects that enable participation in cultural traditions spanning multiple generations, but exceed what should be necessary for immediate survival planning. Human temporal cognition seems specifically designed for maintaining long-term cultural institutions rather than short-term survival planning. The consciousness that emerges from human neural activity includes subjective experiences of meaning, purpose, and transcendence that seem to exceed what should be necessary for biological survival and reproduction. Human consciousness includes capabilities for contemplating abstract concepts like infinity, eternity, and ultimate reality that serve no obvious biological functions but enable participation in sophisticated philosophical and spiritual traditions. The evidence from human biology, psychology, and cultural capabilities suggests that humans possess characteristics that are specifically adapted for life in technologically complex societies rather than natural environments. These adaptations enable sophisticated cultural development while maintaining dependencies on technological and social systems that prevent expansion beyond planetary boundaries. The pattern suggests that human evolution might have been guided or modified to produce beings capable of developing advanced civilizations while remaining contained within cosmic boundaries that prevent detection of or escape from their managed environment. The modifications would enable cultural and intellectual sophistication while maintaining biological and psychological dependencies that ensure continued containment. The observational evidence from astronomical research reveals patterns in cosmic structure and stellar behavior that seem calibrated to maintain conditions suitable for life while preventing the detection of artificial management or intervention. The cosmic microwave background radiation shows temperature fluctuations that had to be precisely calibrated to produce the galaxy structures observed today, yet these fluctuations show no obvious signs of artificial intervention. The distribution of galaxies and dark matter throughout the universe shows patterns of organization that seem too regular to be entirely natural, but not so regular as to obviously indicate artificial construction. The cosmic web of galactic filaments and voids shows mathematical relationships and structural patterns that parallel those found in designed systems, but could potentially be explained by natural processes. The stellar populations observed in our galaxy show age distributions and chemical compositions that seem optimized for the gradual development of planetary systems suitable for life, yet the processes that created these populations operated over timescales that seem to preclude direct management by technological civilizations. The stellar nurseries and formation processes seem guided by invisible influences that operate through natural mechanisms. The planetary systems discovered around other stars show characteristics that make them unsuitable for complex life while leaving our solar system as an apparent anomaly in its suitability for biological development. The hot Jupiters, eccentric orbits, and multiple star systems that characterize most exoplanetary systems create conditions that would prevent the development of stable planetary climates needed for complex life. The The apparent rarity of Earth-like conditions among known exoplanets might indicate that such conditions require artificial intervention or maintenance rather than natural formation processes. The precise combinations of factors needed for complex life might be so improbable that they only occur in artificially maintained environments like cosmic zoos or nature preserves. The radio emissions detected from space show patterns that are consistent with natural astrophysical processes but lack the obvious technological signatures that would indicate advanced civilizations. The pulsars, quasars, and other radio sources that populate our galaxy emit signals that follow natural patterns, rather than showing the regularity or information content that would characterize intentional communication. Yet the absence of obvious technological signatures might itself indicate artificial management designed to prevent developing civilizations from detecting the presence of advanced intelligences. Advanced civilizations might use communication technologies that are undetectable by species at our technological level, or they might deliberately avoid communications that could be intercepted by developing civilizations. The search for extraterrestrial intelligence efforts have systematically scanned the cosmos for artificial signals, but have found only natural radio sources and occasional unexplained anomalies that don't repeat or show obvious technological characteristics. The silence might indicate that we are alone in the universe, or it might indicate that any advanced civilizations that exist are deliberately maintaining radio silence to avoid detection. The space exploration efforts conducted by human civilization have revealed a solar system that seems perfectly designed to support human development, while preventing easy expansion to other star systems. The planets and moons of our solar system provide just enough resources and challenges to motivate space technology development while maintaining barriers that prevent rapid expansion beyond the solar system. The asteroid belt provides mineral resources that could support space industrialization, but requires technological capabilities that remain just beyond current reach. The outer planet moons offer potential habitats and fuel sources, but at distances that require sustained technological development to access. The configuration seems designed to encourage gradual space development while maintaining containment within the solar system. The interstellar space that surrounds our solar system presents conditions that seem calibrated to make interstellar travel extremely difficult, but not obviously impossible. The cosmic ray environment, interstellar dust density, and gravitational fields create obstacles that require technological capabilities far beyond current human reach, but not beyond theoretical possibility. The nearest potentially habitable star systems are located at distances that require travel times measured in centuries or millennia using any currently conceivable propulsion technology. The distances are large enough to make interstellar colonization practically impossible, but small enough to remain tantalizing goals that might motivate continued technological development. The evidence suggests that our cosmic environment has been carefully calibrated to enable the development of advanced technological civilization while maintaining barriers that prevent expansion beyond carefully controlled boundaries. Every aspect of our situation seems optimized to encourage sophisticated cultural and technological development while preventing escape from or detection of our cosmic containment. The mathematical precision required for all these factors to align by pure chance is so extraordinary that it effectively rules out coincidence as an explanation. The alternative theories that might explain these patterns, infinite universes, impossible luck, or fundamental gaps in scientific understanding, all require assumptions that are at least as extraordinary as the zoo hypothesis. The zoo hypothesis provides a coherent framework that explains all the observed patterns with a single theory. We are living in an artificially maintained cosmic preserve, designed and managed by intelligences whose capabilities and purposes remain beyond our current understanding. The preserve enables the development of intelligence and culture while maintaining invisible boundaries that contain and protect developing civilizations. The implications of this possibility extend far beyond academic speculation about cosmic phenomena. If we are indeed inhabitants of an alien zoo, then our understanding of reality, consciousness, and human potential might be fundamentally incomplete. The limitations we experience might not be natural constraints, but artificial boundaries that could potentially be transcended through appropriate knowledge and capabilities. The search for evidence of our cosmic situation becomes not just a scientific investigation, but an exploration of the deepest questions about existence, consciousness, and the nature of reality itself. Whether we discover that we are truly free explorers of a natural universe or carefully maintained inhabitants of a cosmic terrarium, the answer will transform our understanding of what it means to be human and what possibilities might await us in the vast cosmos that surrounds our small world. The question of whether we are inside an alien zoo may ultimately be a question about the nature of existence itself, whether consciousness and intelligence emerge randomly in a chaotic universe, or whether they are carefully nurtured phenomena that require protection and guidance from intelligences whose wisdom and capabilities transcend anything we can currently imagine. The answer to this question will determine not just our scientific understanding, but our philosophical and spiritual comprehension of our place in the cosmos and our potential for growth, development, and transcendence that may extend far beyond the boundaries of our current imagination.